Hello everyone and welcome. In this video we're going to be looking at how to represent signed numbers using 2's complement. We're going to look at how to convert negative denary numbers to 2's complement and how to convert 2's complement numbers back to denary. The steps in converting a negative denary number to 2's complement are as follows. So the step 1, you find the binary value of the equivalent positive denary number. Once you've done that, we'll move on to step 2, where we then convert the result of step 1 and change all the zeros to ones and all the ones to zeros. And then finally in step 3, we then add 1 to the result of step 2. Let's look at an example. In our first example, we're going to look at how to convert -5, a very simple number, to binary using 2's complement. To do this, I'll write down my number sequence: 1, 2, 4, 8, 16, 32, 64. Now, unlike sign and magnitude, with 2's complement, we would write 128. Remember, from our step 1, we have said we just need to find the binary value of the equivalent positive denary, which is 5. So, this will be 0, 0, 0, 0, 0, 1, 0, 1. Then, if we look at step 2, we now need to change all zeros to ones and all ones to zeros. So if we flip them, 0 becomes 1, 1, 1, 1, 1, 1 becomes 0, 1, 0. That's step 2. Now step 3 is to add 1. So we're going to add 1 to this value here. We're going to add 1 to the value here. And if we add 1 to that value, we will be left with just 0 plus 1, which gives us 1. Then we have 1, 0, 1, 1, 1, 1, 1. So -5 in denary, when represented to binary using 2's complement, we have 1, 1, 1, 1, 1, 0, 1, 1. This is our final answer. Let's look at another example. In this example, we're going to convert -112 to binary using 2's complement. Again, to do this, we'll write down the number sequence: 1, 2, 4, 8, 16, 32, 64, 128. Now, if you remember from step 1, we said we find the binary value of the equivalent positive denary number. So 112 to binary will be 0, 1, 1, 1, 0, 0, 0, 0. Step 2, we know we have to flip our zeros to ones and our ones to zeros. So with this value here, this will become 1, that will become 0, 0, 0, this becomes 1, 1, 1, 1. And the third step is to add 1 to this result here. So we're going to add 1 to this value. So if we add 1, So the value there, we will then have 1 plus 1 is 0 carry 1, 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 0 plus 1 is 1, and then we have 0, 0, 1. Okay, so minus 112 when represented in binary using 2's complement, we have 1, 0, 0, 1, 0, 0, 0, 0. And finally, in our third example, we're going to look at converting. Let's do, in our third example, we'll look at 56. Let's convert 56. You might say plus 56. They might write it in your exam as just 56 or plus 56. To do this, we only need to represent 56 into binary. So we would only need step 1 for this. So 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. Because it's a positive value, we only need step 1. So all we have to do is just 0, 0, 1, 1, 1, 0, 0, 0. So that 56 using in denary represented in binary using 2's complement will be 0, 0, 1, 1, 1, 0, 0, 0. That's our final answer. Now, one thing to note when working with 2's complement values is that the number range is slightly different from the number range of sign and magnitude, ever so slightly. So with 2's complement, the number range we work with when working with 8-bit values is between minus 128, which is the smallest negative value we can have, to the biggest denary number value we can have, which is 127. So that's our number range when working with 8-bit values using 2's complement. Now, if for example we're asked to convert 2's complement number to denary, one method you can use can be broken down into the following steps. So the first thing you want to do is to make note of the sign of that 2's complement value. So if for example we know if that value is 1, 0, 0, 1, 0, 0, 1, 0, for example, you make note of the sign. We know in 2's complement, if a value begins with 1, we know that it's a negative value. And if we have a value like this, for example, 0, 1, 1, 0, 1, 0, 0, 1, if it begins with 0, we know that that value is a positive value. So you make note of the sign. The second thing you then want to do is flip the bits. So you flip the zeros to ones and the ones to zeros. Then the second step is to add 1 to what you flipped here. Once you've done that, you then go on to work out the denary equivalent and add the sign. So once you've worked out the denary equivalent of the value, you then go back to add the sign. Now let's convert the following 2's complement value to denary. The first example we're going to look at is we're going to convert 1, 0, 1, 0, 1, 0, 1, 0 to denary. with step 1, we said we should identify what sign this value is. It's always good to make note of this. And remember, it's a negative number. So, if I write down the value again, just space it out so it's clearer. With step 1, we're saying up here that we flip the bits, so zeros to ones and ones to zeros. So this 1 here will become 0, 1, 0, 1, 0, 1, 0, and 1. In step 2, we're saying we need to add 1 to the result of step 1. So we're going to add 1 to this value here. We're going to add 1 to this value here. So if I put 1 there, we're just adding 1 there. So 1 plus 1 is 0 carry 1. 0 plus 1 is 1. There's nothing else to add there, so I'll just bring down this value. So 1, 0, 1, 0, 1, 0. And in step 3, we're saying we need to work out the denary equivalent of this value. So for step 3, I know the numbers I need to add will be 64 plus 16 plus 4 plus 2. And if I add all of these numbers together, I'm going to get 86. Now don't forget, in our step 1 here, we took note that this 2's complement value we're working with is a negative number. So we put our sign here. One thing you should note is always remember that with 2's complement values, the first value there, if it's 1, it means it's a negative number, and if it's 0, it means it's a positive number you're working with 2's complement values. It doesn't matter what the bits are, if it's 8 bit, 16 bits, 4 bits. If that most significant bit there is 1, it's negative, and if it's 0, it's positive. Okay. Now, the second method I'm going to introduce you to, with this method, I've split this method into 2 steps. So with this method, all you have to do is you place this step. So step 1, you use the place values. So use the place values. Our place values would 2, 4, 8, 4, 2, 1. Okay. And then make note of your most significant bit. If it's 1, it has to be negative, and if it's 0, it's going to be positive. And in step 2, all you have to do is just add up place values again with 1. So what do I mean by that? So in our second example, let's say you're asked to convert 100111010 in 2's complement to denary. If you're asked to do this, now step 1 here, we said use place values. So we use our place values, but making note of our most significant bit. So to use our place value, I'm going to say 1, 2, 4, 8, 16, 32, 64. I'm working with 8 bits here. Now this is a negative value there. It therefore means that my most significant bit is a negative number, so I'm going to say minus 128. So I put the values there. I have 1 0 0 1 1 0 1 0, and if you add all of these together, you would have minus 128 plus 16 plus 8 plus 2, and this will give you minus 102. So that's the second method. So just be mindful of your most significant bit there. If it's 1, that value becomes minus 128. Obviously, if it's 0, it doesn't matter, because we won't be needing the minus 128 in our calculations here. Now, we said that 2's complement is much more better when performing arithmetic operations, as against using sign and magnitude, which does not work very well with arithmetic operations. To prove that, we're going to do, let's do a simple problem here to prove that 2's complement actually works very well with these arithmetic operations. So let's say we are asked to solve the following: minus 83 plus 30. Okay, so first things first, we convert minus 83 into its 2's complement form. To do that, I'm going to use the first method. So with that first method there, I know that minus 83 is going to be 0 1 0 1 0 0 1 1. Then if we flip the zeros and the ones, so I have 1 0 1 0 1 1 0 0, and then we add 1. If we add 1, this will give me 1 0 1 1 0 1 0 1. So this represents minus 83. I know that plus 30 is 0 0 0 1 1 1 1 0. So if we go on to add these two values, so plus 30 minus 83, so if I put minus 83, which is right there, so this is minus 83. If I go on to do that, what I then have is 1 0 1 0 1 1 0 1. So plus 30 minus 83. Do not forget that plus, this is the same as saying plus 30 plus minus 83. So if I add both together, I should have 0 plus 1 is 1, 1, 1 plus 1 is 0 carry 1, 1 plus 1 plus 1 is 1 carry 1, 1 plus 1 is 0 carry 1, 1 plus 1 is 0 carry 1, 0 plus 0 plus 1 is 1, 1. Okay, and if you convert this value, you should have minus 53. See, it works very well with arithmetic operations.